he's going to talk about a special topic in this context today. It's about linear friction welding of aerospace components. Mr. Kallee, you can start.
Thank you much for the nice introduction. I hope you can see my screen.
Yes.
I want to focus on 9 topics on linear friction welding of aerospace components. That's a process that's increasingly being used for near net shape manufacturing. So it's an advanced manufacturing process, not additive manufacturing, but adding little blocks to aerospace parts and then machine them to the final shape. First, I want to focus on the principal materials and applications, and then on the motion, machine, and quality, and finally on the design variants, and I will conclude with the benefits and limitations. Linear friction welding works in a way that you rotate or you oscillate 2 parts against each other. So it's similar to rotary friction welding, but it can be used for rectangular parts. So I have some parts here. Fortunately, we can't really show them that easily today, but the idea is that we produce pre-manufactured parts from various materials. For example, from titanium, like we show the blades here, or from stainless steel. And the way how to do that is that we use a reciprocating motion while pressing the parts together with a very high force. Here you see some titanium being welded from the left to right. You see initial contact, and then a flash or burr is being expelled. And finally, the material cools down. The big advantage is, as it is a solid phase welding process, we do not melt the materials. We stay below the melting point of the materials, and we don't even need to apply gas shielding even in the case of titanium. And as you see, we can get a very nice microstructure. Yeah, the limitation is there is still a flash or burr on the left and right of the weld that needs to be machined off after welding. It's a process that is very stable and it is used by all aircraft manufacturers. It's a very effective process indeed. The process can also be used for aluminium. In the case of titanium, you have a very low heat conductivity, so the heat really stays in the area that we want to process. In the case of aluminium, it's more difficult because the heat is being sucked into the workpiece. So you have to have a really clever parameters, and you get a wide flash, as you can see here on the left-hand side. It is possible to weld dissimilar materials, for example, welding copper to aluminium. And it is certainly possible to weld steel, and even in the automotive industry. However, the main applications are due to the cost of the material in the manufacture of titanium components, and that is what I want to focus today on, is bladed discs, or so-called blisks, either in the initial manufacture to save material. Instead of machining from solid, we machine a pre-manufacture or a near net shape part, and then we machine to the final shape. What you can see here is the aero-engine fan blade of or blisk of a Eurofighter engine. So the typical applications are in the military aircraft. And I have to tell you, the shape of the blade is not perfect for aerodynamics. It is a compromise between the possibility of repairing that product by linear friction welding and the optimized airstream of the part. So at the bottom of the blade, where the blade joins the disc, it's a little bit wider than it would be absolutely necessary, but we will focus on that on the design stages later. I have heavily tried to get the process implemented by the stationary gas turbine manufacturers who use very specific stainless steels, and these are expensive as well. However, they don't see the cost advantage as significantly as the titanium uses. So I'm not too much aware of stainless steels being welded in the stationary turbine business. But as you know, with these very expensive and very complicated processes, you don't talk about broadly about what you do. So, for example, it's an ideal process for repair blades. What we want to focus on is near net shape manufacturing, advanced manufacturing. What you see on the right-hand side is machining a turbine blade from solid. So quite a lot of swarf is being generated. That material can be recycled, but it has not the original value. And we see also that it's time consuming to machine off these large amounts of titanium. So in the top picture, number A, you see machining from solid. A little block is used, and then, for example, a little fan blade is being machined. But what we propose, and that is being used now, is in picture B at the bottom. We want to weld a block by linear friction welding to workpiece number 1. And then finally, we machine the part to the shape or the dimensions that are required. And by that, we first of all get rid of the flash. We get rid of any kissing bonds or unwelded regions at the edges of the workpiece. And we have finally a part that meets our specification. Here you see an aerospace part on the right-hand side that has been made from 3 components. Little blocks onto the substrate, and then finally we machine this little bracket or tab out of the component, and the weld integrity is so high that it is nearly not possible to distinguish it from the material of the parent material. So we have a very refined microstructure and very high strength. So in titanium there is no significant decrease of strength in the weld area. The main purpose is to improve our buy to fly ratio. So how much material do you have to buy, and how much is being machined off during machining by high-speed CNC machining being generated into swarf, and then you check the weight of what will finally fly in the aircraft. That is the buy to fly ratio. Here a similar component, I think you can see by now, this is the little block that was twice as large, has been welded to the substrate and then finally machined off. You see here the swarf, the swarf or the burr or the flash being generated, and that needs to be machined off, otherwise it would be a stress razor for fatigue properties. Without some simple automotive applications, the swarf or the burr or flash is normally being machined off. Here we see a part that consists out of, I think I counted it was 11 parts on the right-hand side. You see all of the 11 parts. I think you understand the concept. So it's a reciprocating motion where the smaller parts are being vibrated against a stationary kept part. The part in the middle is kept stationary, and they are pressed with a high force onto the workpiece. Why do we need the high forces? In solid phase welding, we want to stay below the melting point of the material. And by that, it's more like a forging process. It's more like a process where you, like making this Damascene steel, the swords, forge welding, fire welding, where material just gets hot. And at the end of the cycle, and we come to that in a second, we will increase the pressure to get all this plasticized material pressed into the flash or burr. Here you see some rocket fuel tanks made at TWI, the Welding Institute in Cambridge, England. These are made from titanium, and typically this is a very large dome, for example, which needs to be bolted to another aircraft structure. So here you see the bolt holes, and to make that, we use linear friction welding very effectively to process titanium parts. The largest linear friction welded part was, a component that was near net shape component. And you see the figures here, a very little material wastage. The machining time has been reduced. And we were able, although this seems to be similar to military components in military aircraft, we were able to exhibit that in Birmingham. But indeed, the military aircraft industry is the ones that use the process the most for near net shape manufacturing. And they don't talk about what they really use it for, but for similar components like shown here. I have an idea to use it also for titanium heat exchangers. So in some hot areas, titanium is the material that you choose. I'm speaking also about the glass conduction, for example, how to get the cables through these parts. That's big business, and instead of attaching with a rubber seal a little lid, you could easily use linear friction welding to attach a lid to the heat exchanger. Not in the aerospace business, but in the manufacture of chains in Austria, in Styria, a company called PEWAG uses the process to make links of chains, heavy-duty chains, for example, snow chains in the smallest area that they do, but they do larger chains as well. And you see they have two different types of links. The solid link is a complete part that is forged, and then there are parts that are made from two half parts to be welded by linear friction welding. I could introduce you to PEWAG, a very interesting application. And this is the unusual thing. They use it for steel. Another steel application is making wheel rims for agricultural vehicles or excavators, where the big hub of the wheel is being linear friction welded at the top. A dream coming true is going on in America at our friends at Edison Welding Institute, Jerry Gould. This is, instead of using flash butt welding, which has advantages and limitations, using linear friction welding for making rails. Rails, instead of using thermite welding, either in the factory to make long welds that cannot be made in one part and then transport them onto site, endless rails to be made in the factory as shown here, but ideally even with a portable machine to be done on the construction site to join the high-speed rails. I have had a good look at this machine. We will see later on how the principle in generally works, but here we have a mechanically driven machine. So the oscillation is done by a large electrical motor and a flywheel, and only the pressure is applied by hydraulic actuation. What type of forces are necessary? You see here the up and down movement or forward and backward movement. That is what we call the in-plane force. Reciprocal motion is being generated. We need a relative motion between one stationary part on the right and one vibrating or reciprocating part on the left. And then we have the axial force, and that goes up to a region of 150 tons in typical commercial applications. So the blue rail track welding machine, that is a machine with 150 tons. You see 4 different phases: initial contact phase, where the material just gets hot by friction, and then conditioning. So the spikes of the material have already been worn out, and now we have a sliding contact with in the burn-off phase with a plasticized layer in between. The flash is being generated, and then we stop the reciprocating motion. You see the red arrow disappears, and the 2 parts are carefully aligned against each other, and the forging force is applied. This is typically at least 20 or even 50% higher than what we use during the reciprocation. There are two different concepts of motion possible. You see here on the left-hand side, that is the recommended movement, the lateral movement over the short edge of the part. And the longitudinal motion is not really that ideal for having perfect metallurgical properties. But in some cases, it cannot be done differently. For example, if you have access difficulties, like on these turbines, there you use typically what they call then the chordal movement along the long axis. Other ideas would be to use tangential or perpendicular. So there's a lot of know-how, and you see even patents involved in having the right choice here. You see two flags. The dragon is representing Wales. Dave Nicholas and Wayne Thomas were at TWI, the Welding Institute, the leading investigators in getting the methodology and the parameters right on friction welding. And on the right-hand side, you see Edward Watts, a very capable technician who got the machine operated. The machine has been manufactured by blisks Equipment, a company that focused on supplying the coal industry initially, and then focused on rotary friction welding and linear friction welding, and transferred the know-how then to Thomson, what is part of KUKA UK, the Thomson friction welding machine. But the most important thing that you learn today is the secret of linear friction welding has been divulged today. The secret is that you do not reduce the frequency at the end of the weld, but you ramp down the amplitude. So the movement gets from plus and minus 5 millimeter, plus and minus 4, plus and minus 3, plus and minus 2, plus and minus 1 to plus and minus 0. That is the way how you can align the components so well against each other. That is difficult. You need a special gearbox to do that. It's not like the monkey on the bike. The monkey on the bike, at the end of his trip, he is with the pedal somewhere in the space, and that's the wrong approach. It will never work to get parts properly aligned. This is a real sketch of amplitudes, forces in red, and burn-off being mentioned. Burn-off, that is the material that is being expelled into the flesh or burr. Burn-off means we measure how much shorter has the part become. So we need to look at that. And here you see that the force in this case has been significantly, the red curve has significantly been increased at the end when the parts are stationary, have been slowed, the amplitude has been ramped down. And then we generate, most of the flash is being generated in that phase at the very end, which we increase the forging force at the end of the weld. I was privileged to be the project leader of a large project, a European funded project on doing non-sinusoidal motion. So with the mechanical system, like the monkey on the bike, you can only do a sinus wave, but we wanted to start having hydraulic actuation, first of all, for cost saving, and second of all, to have a cheaper, for cost saving and a cheaper system, and a more versatile system where different type of modes could be driven. But let us focus first on the mechanical systems that have been built. This is a complicated gearbox, and on the left-hand side, we see the linear motion being generated, so plus and minus, let's say 3 millimeters of amplitude. And on the right-hand side, we see that beam only swivels around that pivot point. So this pivot point does not move up and down anymore. And to achieve that this goes really to 0 at the end of the weld cycle, we just use 2 excenters on the same shaft, which is driven by an electrical motor from the side. And if you align them in a way that they are misaligned, then the beam swivels. And if they are in phase and then being rotated, as shown here in the left-hand picture, then this whipple beam moves up and down or forward and backward. And the British idea was to use, instead of using bearings that could wear out is to use a flexible element like a blade. And as far as I remember, only one of these blades has ever broken. So that was so well designed that the whole machine was fully balanced, and you could put a coin standing on its edge on top of the machine without the coin tipping over during the process. Here you see the electrical motor that drives this electrical system. You see a lot of hydraulics, of course, involved in applying the forging force. The in-plane force in the joint area, that is being generated by electrical means. It's a noise-proof cell. In this case, the machine is not on rubber elements discoupled from the floor, but it generates by some vibration. And I had my office just above that machine. You didn't need to ask which customer's product were just being processed. So you could just hear from the welding cycle what type of material was being processed, or you knew, of course, in the background which parts were then made. So we made a lot of prototyping parts that has been then assessed by the clients. Was big business at the time, just producing metallic combinations of different types to check whether this process could be used in the aero engine manufacture. There were only 3 machines being sold worldwide of this mechanical concept. One of them is at MTU in Munich, and one of them, this is Plex equipment machines. One of them is in TWI, and the third is at Rolls-Royce. So 3 machines, because they had an investment value of, let's say, some over 3 million pound. So they were nearly 5 million euro with all the tooling that goes with them. So here you see, for example, the machine at MTU that has been built by Plex equipment. And you see the flags in the background. There's a Stuttgart flag. Oh, this is not for MPA, I have to say. This is for Rudolf Reinhardt of Mercedes-Benz, who provided knowledge on rotary friction welding and fixturing. And the tooling that you see here, that is, if you see that once, not everybody can access that room. This is really impressive stuff. And then we see the Welsh Dragon for Davis Nicholas, and we see the Union Jack for Roger Black. This was a very nice collaboration in the, I would say, late 70s, early 80s, where linear friction welding has been transferred from the United Kingdom to Germany. Yeah, and MTU was in a delightful position to produce the fan blades of the Eurofighter aircraft. You see again these little blocks which are necessary for clamping the parts. And more than 100 linear friction welded aero engines were being built. So this did not go in very high volumes, but of course there are many blades on one disc, and all that with the mechanical machine. Quite impressive activity at the time. And they were very proud about it and published that very well. So these are the blisks, the linear friction welded, the blades to disc combinations that TWI was then exhibiting at one of the fair stands. We, as an admiration for the work that we had provided, we got some very nice samples to be shown. The Americans had a different approach at MTS. It's a hydraulic manufacturer of fatigue testing machines. They thought, oh, we do that hydraulically. And my boss, Dave Nicholas, had the idea, oh, this would generate some cost saving if we use a linear friction welded machine. And we produced the LinFric machine within this European funded project in collaboration, for example, with Reiser in Germany or Zwick-Röll in Germany and England, and Harms and Wende making the control box. So this was a good, one of the very first that started in ECU, 1.36 million ECU, which is similar to a euro at the later stage. What you see in the background is a hydraulic accumulator. So similar to storing energy in a capacitor, electrical energy in a capacitor, we have a hydraulic system that compresses a rubber bladder, like an air balloon, inside that inside these vessels. And so we need some, let's say maybe 2 or 3 minutes to charge up the hydraulic system. And then we have an oil flow of 750 liters per minute for the duration of the weld. This is a very energy saving system being implemented with this energy storage system. Similar to a mechanical flywheel, we use a hydraulic accumulator. And at the time, this was the biggest machine of the world, 150 kilonewton. That's still a big thing. And you see, you could, instead of having this green bar here, you could install, on the previous slide, we could see that you could install a complete aero engine with approximately a meter diameter, instead of using this green bar. Is not part of the machine. That is just a temporary fixture for making smaller type components. By the way, this is me on the left-hand side in younger years, working still hard. Was a tough life. But the idea of this machine was we used hydrostatic bearing. Here you see the fountain in Frankfurt, Palmengarten. And you see that marble ball can flow very easily. You can operate it by hand and it rotates itself. And we adopted the same system. So we have very tiny little tubes through which we feed in oil into, this is a rubber element made from an old tire, I would say, or similar to an old tire. So we have a system where, yeah, friction is being minimized by using these type of hydrostatic bearings. The total budget of this project was only of the machines was thinking that we want to sell them for 750 million euro. And we spent some 7.5 man years just to develop the prototype. The prototype worked on occasions very well, but it has then had some complex challenges regarding hydraulics and a control system. And then Thomson built a replica of that part, and that is being used now at DWI on a day-by-day basis. Thomson industrialized that to the next level, from prototype to industrial machine. These are the Thomson machines. That would be interesting to hear about the history of what they learned out of their experience with linear friction welding. I know what they think about it, and large parts have been made, and I can introduce you to the relevant parties if you ever want. In the United States, everything is a little bit bigger. This is a 19-axle transport. The total weight of the machine, not everything is on the same truck, of course. I think some 10 trucks have been transported to get this machine. This is only the machine bed on the low loader. The total weight of the machine is 181 tons at Pratt & Whitney. So a similar machine is now at Lift in Detroit. Very big machine beds, and they are, of course, put into the floor. Again, I have access to that machine. If you need some prototypes, I will establish the contacts. And one of the most interested users who speaks very little about it is, of course, a company in France, and that is supplied by ACB, Cyril Bath. And they have two different types of hydraulic machines. Here is the open frame machine, and with a significant benefit of loading that by crane. And then we have a machine with a closed frame at the right-hand side. The Chinese are following up, again, with the concept that I have demonstrated with the hydraulic actuation. And the most thing is you need to think what happens if something goes wrong. So bird strikes, you remember that situation in Washington, DC. So then you can do repair. I only want to quickly look at a quality control. So there are 6 different dimensions, and particularly the angles that you have to look at. In Japan, you look only at alpha and beta. The gamma, the third angle, is not really that critical for them. And then we need to look at how to machine these parts before they are welded. So you have this little stub area here. And this is where I said we have the non-optimized geometry regarding airflow, but by that we can easily repair the parts. And sometimes we use buffers or interlayers. And only quickly I want to look at the variance. You can look into the proceedings later, but orbital is a good one. And then translational assisted upset welding. So an electrical current is being used, and only 1, 2, 3, 4, 5, 6 cycles at the end to disrupt the oxides. That's the trick. The oxides are being disrupted by the friction. Low force linear friction welding, again, applying some electrical energy in addition to the frictional heat. And then very common for welding plastics, for example, the different colors of a rear light of a car or of automotive parts in the air duct systems, plastic parts. High frequency pressure welding, have a look at that. And then a system for making window frames, multiple orbital systems near Regensburg or Nuremberg. And just to summarize the benefits and limitations, I want to show it's a solid phase welding process. It's very flexible. It's used for near net shape manufacturing. It's easy and ecologically very friendly. However, it requires some high forces. You need to set up the parts very carefully. It mainly relies on parameter monitoring. So this is not the activity of MPA to look at the weld parts. You need to monitor during welding whether the parameters have been met, and then you know that you have the good quality. And it requires some written welding procedures and ideally a European welding engineer to supervise the welding activities. I think I'm just in time. Thank you much for your interest, and I'm looking forward to discussions.
Thank you, Mr. Kallee, for this very interesting talk about an interesting topic. Are there any questions from the participants? So I don't see a raised hand. Okay, I'm going to ask you one thing, and maybe you already explained it with your last slides, but when you showed the examples in the beginning, where you first made the welds and then the machining after, I had the question if you always do it this way or the other way also. So you first machine the parts to the final contour and then do your welds. So you have both possibilities, or what is recommended, or yeah?
Yeah, most commonly a machining process follows the welding process, because at least you want to remove the flash or burr.
Yeah.
I know in some rotary friction welding applications, in automotive applications, like for example, airbags, you can't remove the flash, so the flash will stay inside the part. And so sometimes maybe the flash stays on the inside. And yeah, of course, we have sometimes hollow blades as well. In most cases, a machining process follows. And if a machining process follows, then you have even this near net shape manufacturing, that you have an area that can be more easily clamped. I don't know anything where no machining would be necessary after welding.
Okay. Thanks for this explanation. Okay, regarding our timetable, I would like to proceed with the next presentation. So thank you again, Mr. Kallee.
Thank you.
So the next speaker is from